The last three examples that we just looked at were polynomials that were relatively simple. In fact, they each had just one term each. When your polynomial has more than one term, the process for finding the derivative is relatively straightforward. All we do is take the derivatives one term at a time, or we sometimes say take the derivatives term by term. In this example here, y has four terms. 7x cubed is the first term, negative 2x squared is the second term, and so on. Remember that terms are separated with addition or subtraction, so that's why we have four of them here. Also notice that the first two terms, 7x to the 3 and negative 2x to the 2, both look like a times x to the n. We can use the power rule on those two terms. So let's go ahead and take the derivative one term at a time. We'll start with the first one, 7x to the 3. The derivative of that term is equal to 21x squared. So of course that comes from taking the 3, the original power, multiplying by 7. 3 times 7 gives me 21. Keep the x, and then reduce the original power of 3 by 1 down to 2. So that gives me 21x squared. The derivative of the second term is going to be negative 4 times x to the 1. If I reduce 2 by 1, I get 1. So 4x to the 1 we're just going to write as 4x. Remember here, the sign in front stays, so we don't just get rid of that. The third term is a line. It's the equation of a simple line, 10x. And we know that for the equation of a line, the derivative is the slope of that line. So therefore, 10x has a derivative of just 10. And finally, negative 9 is a constant term, and we know that the derivative of any constant is equal to 0. So I have four pieces technically to my derivative. The last one is a 0, so we're not going to keep writing that. And so we say that our derivative is 21x squared minus 4x plus 10. That's an equation or a formula that tells me how the original function f is changing. So if I'm given f at the top here of this slide, then this new equation, 21x squared minus 4x plus 10, tells me everything I need to know about how the original function is changing. So we'll explore that more here in a minute. So here we have two more derivative examples. The first one is g of t given here at the top of the slide. Why don't you pause the slide and see if you can quickly jot down what you think the derivative of this function should be, and then pick up the presentation when you're done. Okay, let's go ahead and take a look at what the derivative would be. If we take the derivatives one term at a time, and notice that this function has 5 different terms, we get the following. For the first term, negative 8 times 5 is negative 40, t to the power of 4 from reducing 5 down to 4. So that's the derivative of the first term. The second term has a derivative that's equal to 6t squared. 3 times 2 is 6, and then t squared. The third term says negative 5 times 2 gives me negative 10, and then I reduce the power down to 1. The fourth term is the one that most people miss if they're going to miss it. The derivative of t is equal to 1. Now keep in mind, t can be rewritten as 1 times t. So that's not a constant term. The derivative of that is not 0. T is variable. It's not constant. And so think of that as a line with a slope of 1. 1 times t looks like 1 times x. The slope of that line is 1. So the number in front of a variable where the power is 1 like this, the derivative will just be that number. If that number is hidden like it is here, then we get a 1 for the derivative. And then of course the derivative of 7 is equal to 0. So that's our final derivative. Try it again with p of q here. Maybe pause and then come back when you're done. So the derivative p of q will look like this. 2 times 1.5 gives me 3. the power on q becomes 1. The second term, negative 3.2q, is basically a line. The number in front of that line, the slope of that line, is negative 3.2, so that's the derivative of the second term. And then the slope of negative 40, because it's a constant, is 0. So the derivative of p prime, the derivative of p, which is p primed, is simply 3q minus 3.2.